Today we're going to take a look at logarithmic functions. We will start our look at logarithmic functions with pondering a very special situation. Hopefully this will kind of get you ready for what we're looking at here. 2 to the power 6 is 64. 2 to the power 7 is 128. So if we want to figure out what exponent on 2 will make exactly 100, we should be able to tell that since 2 to the 6 is 64, since 2 to the exponent 7 is 128, that x is going to be somewhere between 6 and 7. And we can fiddle around with values. We could try 6.4, 6.5, 6.45, 6.46, 6.47. We can play around with all different types of values, but that kind of strategy would be called guess and check. That sort of strategy would take a long time, and it would be hard to get an exact answer. Now, the lesson does say take a minute to try and figure out what it is, but we'll skip that because today is a bit of a crazy day. If you want to try one value on your calculator, you can. If you want to try two values, you can. I'm not telling you not to. But what we're trying to do is we're trying to figure out what exponent on 2 makes exactly 100. What is it? Now, it looks like Sky's trying something. Not sure what Alana's doing. So as Alana and Sky are trying, well, you fiddle with numbers. You get closer and closer and closer and closer. But we are going to kind of, wherever you are, whether you're really close or whether you think you still got some ways to go, we are going to kind of cut that off there only because we got some more math to figure out here. Today we are going to explore a new type of function where we can answer that question quickly and effectively. Okay? We can answer that question quickly and effectively. And you know what? We can actually use Desmos or the graphing calculator really easily here. Like if I pop open Desmos, I can do 2 to the exponent x. I can do y equals 100. And I can go ahead and see there's a point of intersection there. And I can click on it and I can see the value of 6.644 to 3 decimal places. 6.644. That's the answer. So while I said that some things are time consuming, Desmos is not time consuming at all. It could tell us the answer quickly. But even still, we're not here just to use Desmos today. What we're actually here to do today is we're here to talk about logarithmic functions. So what we want to do is we want to get some information on some definitions and what certain things mean. So to isolate x in the exponential function y equals a to the exponent x, you need to work backward. In other words, you need to find the inverse function of y equals a to the exponent x. This mathematical dilemma was solved by John Napier, who lived from 1550 to 1617. And what he did was he developed the logarithm. So he is credited with developing this very important mathematical concept. If we take a look at the expression 2 cubed equals 8. We can write this with logarithms. An exponent or a power has a base and an exponent. Well, a logarithm has a base as well. So what we can do is we can focus in on 2 cubed equals 8, and we can draw or write a logarithmic expression that is mathematically equivalent to this, but in terms of logarithms instead of exponents. So an expression that uses logarithms instead of exponents that says the same thing is this right here. The log base 2 of 8 equals 3. The log base 2 of 8 equals 3. That's the exact same thing. It's telling us the exact same thing. We're still using the 2, the 3, and the 8, but we're using them in a different way. So if we take a look at a logarithmic expression, like this, the 2 is the base, and what the 8 tells us is this. Because we're trying to figure out what the log base 2 of 8 is, that's what we're asking. We're asking 2 to what exponent gives us 8? 2 to what exponent gives us 8? Well, the answer is 3. 2 to the exponent 3 gives you 8. Okay? Now, sometimes we'll see a log, but we won't see a base. If we see the word log, but we don't see a base, then we assume that the base is 10. Your calculators do have a log button on it. The graphing calculator, the log button is right next to the 7. On my classroom calculators, there's also a log button. On a calculator on an iPhone, there's also a log button. All these logs are base 10. Always base 10 for the button that says log. Now what we want to do is we want to just see how we understand that. In other words, what we want to do is see if we can translate 3 squared equals 9 into a logarithmic expression. Okay? So how we do this is simple. Once you get used to it, it's simple anyway. We would write this as the log. The base would be the same base as the exponent, so the log base 3, but it's the log base 3 of 9. The 9 comes next, and we know that the log base 3 of 9, or 3 to the second power, is 9, so the answer is equal to 2. So the log base 3 of 9 is equal to 2 is an equivalent logarithmic expression to the exponential expression given as 3 squared equals 9. Now we're going to kind of spice it up again. We're going to say a to the exponent b equals c. What's the base? It's a. So the base is the same when we write out as logarithm. So it's going to be the log base a of what? C, and that's going to equal b. Now, your calculator can figure out the base 10 logarithm. If you want to find out any other logarithm, use the following trick. So what's the log base 2 of 100? That's what we asked at the very beginning of this lesson. How can we figure this out using the calculator? Well, here's what we have to do. With the calculator, what we will do is this. And understanding that your calculator always uses log base 10 if there's a log button. But what we can do is we can write the log of 100 divided by the log of the base. Now the base is 2, so we're going to write that as the log of 2. So if we take the log of 100 and divide it by the log of 2, then we'll figure out the answer to that question. And we already did this using Desmos. We saw that it was 6.645 or something like that. So that's what we should get when we do this. So on the graphing calculator, we would just go to the home screen and then just type in log of 100. Now it does start with a left bracket, so you have to close with a right bracket, then hit divide, and then log of 2, and then right bracket, and hit enter. You get 6.64, just like we got before. 6.64, right? 6.644, which is exactly what we got with Desmos. So that's how we do it. Divide the log of 100 by the log of 2. But you know what? I haven't tried this, but I think Desmos does the same thing. If I go to Desmos and I go to functions, and I type in log of 100, and then I divide that by the log of 2, I'm not graphing anything with Desmos. I'm just typing in log of 100 divided by log of 2. Desmos tells me the answer. So Desmos is a calculator as well as a graphing tool. Desmos will tell you the answer if you write it out as a log of 100 divided by log of 2. Desmos can also do that calculation for you. Okay. So again, we already knew the answer from before, but we get 6.64 if we write it to 2 decimal places. Now, what's the log base 7 of 100? The log base 7 of 100. Well, again, we're going to take the log of 100 and we're going to divide it by the log of the base, which is 7. So whether we use Desmos to do that or we use a graphing calculator to do that, we need to figure out the log of 100 divided by the log of 7. So log of 100 divided by log of 7. And the answer is 2.37 if we write it to 2 decimal places. That is the log base 7 of 100. Okay? Questions? Okay. A lot of what we do in this relations and functions unit is graphing. So a lot of what we need to know are properties of the function. Properties of the function. So this graph is a lot different than the graph of the exponential function. But while it's a lot different, it's also very similar. So if we take a look at the graph here. What we see is the graph comes close, but never touches the y-axis. It comes up and generally has an x-intercept of 1. There's no y-intercept. Okay. The range is all real values. And the domain is anything bigger than 0, not 0. If you try and find the log of 0 on your calculator, it's going to bark at you. It's not going to like you. You can't take the log of 0. So this function is not defined when x is 0 or when it's negative. You have to enter a positive number for x to get an answer. Okay? What else do we see? Well, the base of a logarithm can be any number other than 0. Now, to be honest with you, we are probably only going to deal with one or two different types of bases, but it's still important for you to know what they look like and how they're going to appear. And if we're going to compare two graphs, like say the log base 2 of x and the log base 3 of x, the one with the smaller base grows quicker. So of the red and the green graph graphed together on the right side of the page, the green graph is going to have a smaller base. We might not know what that base is, but it's going to be smaller than the base of that of the red curve. Okay? If the base is e, now what is e? E is like pi. It's a constant. It's a number that we're always know what it is. E is 2.718281828 ba 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 ba. We don't write it as the log base e of x. We write it as ln of x. And all calculators, even scientific calculators, have an ln x button. So if you go to the graphing calculator, the ln button is just underneath the log button, and it's just to the left of the 4. That is the ln button. Now the ln, or the ln, really is the natural logarithm. The natural logarithm. So when we are looking for the log base e of x, we're actually talking about the ln of x. And the most important type of logarithm for this course is the ln of x. The ln of x is going to be what we use when we come up with regression equations next class. If any of you go on and take pre-calculus or even calculus, you will talk about the natural logarithm. The natural logarithm is the most important one that there is, 100%. Okay? So now what we want to do is we want to graph the following function. Y equals 4 log x. Y equals 4 log x. So, to graph a logarithm, it's important that you're aware what the base is. What's the base of this log? No, no. If there's no base, what's the base? 10. The base is 10. So because the base is 10, I'm going to tell you something. It makes sense if our x values are powers of 10. Powers of 10. So that means that x could be 1, x could be 10, x could be 100. We can make a nice clean table of values if we use powers of 10 as our x values. We can use other values, it's just not going to be nice. So what I would do is I would create a table of values. I would start at 1, 10, and I'd even just probably go up to 100. I'm not going to go crazy with this because there's no reason to go up to like 1,000 or anything really silly. Now for y, what we could do is we could figure out the y value in each of those cases. And again, the graphing calculator is awesome because if I go to the graphing calculator and I type in, go to my y equals, and I clear stuff that's there. But if I go to my y equals and I type in 4 log x and I close the bracket, I'm typing in 4 log x. What we can do with the graphing calculator is we can create a table that's going to tell us these values. Okay? So If I go second table set, I'll start at -3. Sure, I'll start at -3. Okay? And I'll go up by ones. So I'll go to my table. And I see that at 1, it has a value of what? 0. So at 1, it's 0. Now, what's its value at 10? So if I go back to my graphing calculator, I can cursor down until I get to 10. And at 10, we see the answer is 4. So that's a 4. Now, what's the answer when we get to 100? Yep. And how we would get there quickly here is I could type in, I can't even type anything in, but what I can do is we can go to second table set, and I can tell it now to start at 100. And then I go back to the table, and it'll go at 100, and it'll give us 8, just as Alana mentioned. So we're going to put 8 here. I've got 3 points, so I can graph this. The important thing is to graph this consistently. In other words, here's 50, here's 100, here's -50, here's -100. My y's go up to 10, so I might as well just go to 10 here. This is -10, and then you're going to try and plot your points. So at 1, it's 0. So 1 is going to be this really point that's close to the y-axis, but not on the y-axis. 10 is going to be here, and it's going to give you this right here, 10, 4. 108 is going to be right here. So what it's going to give us is a curve that's hugging the, that's not hugging the y-axis. That's on the y-axis. We want something that's hugging the y-axis. I'm still buggering that up. Hugging the y-axis and then coming out, and then going like this. And there should be arrowheads going in both directions, both down and up and to the right. So that's what that logarithm function looks like. And you know what? If you actually look at that graph, that graph actually looks a lot like how we drew the graph of an exponential function. It does. We would have to rotate it a bit, but if you rotated it a bit and maybe did a reflection, that graph would be just like an exponential function graph. It just looks different. Okay? So if you're graphing a logarithmic function, it pays to use x values that are powers of the base. The base here is 10, so that's why you use 1, 10, and 100. Now let's do part B. The x-intercept, the y-intercept, the end behavior, the domain, and the range. So, what's the x-intercept? X-intercept's at 1. What's the y-intercept? None. What's the end behavior? Quad 4 to quad 1. Yep. What's the domain? I would write the domain as 0 to infinity, round brackets on both, and then -infinity to infinity for the range. Okay? Now, we can sometimes make some changes to what the logarithmic function looks like by making changes to the equation. But if we're just looking at something that's the log base something of x, then that's what we're going to get, even if we multiply by 4 or multiply by 2. Okay? What about if we want to graph -10 ln x? negative 10 ln x. And ln is the log base e. So I wouldn't get too hell-bent over coming up with nice table of values, but what I would do is I would punch the equation into your technological tool, and I would try and find some key points off the graph. So if we go y equals, we type in negative 10 ln x. And now we do have to set a window though. So what kind of window are we going to set? So just a second, I've got a phone call. On Desmos? On Desmos, you want to go to functions, miscellaneous, and the ln is right here. Now I don't know exactly what it looks like on the ln. Yeah. Okay. So we do have to kind of come up with a window here. The window is going to be kind of interesting to find. Negative 2 is fine for x. I would probably go no more than to about maybe I might even just be okay to go from negative 1 to like even like 5. For y's. Now this graph is, you'll find out this very quickly, but it's actually a negative graph. So it's in the fourth quadrant is what I'm getting at. So because it's in the fourth quadrant, how I would go with this is I might go from, say, negative 200 to, like, say, maybe 20. And I'd go up by, like, about tens, roughly. And I'm just going to turn my stat plots off because they'll interfere with what I have here. Then I'm going to hit graph. And actually, when I do that, I notice that that's not the brightest move that I've ever made. We do need to go into quadrant 1. So I'm going to go to window here. And I'm going to go from negative 200 to 200 maybe. Or not even. Maybe negative maybe 50. Negative 50. One to 4. And we're going to go up by tens even. So hit graph. There we go. That's what the graph looks like. Now, the graphing calculator is a funny beast because it looks like this graph actually stops, but it doesn't. It continues to go up the y-axis, but never touches the y-axis. It never touches the y-axis. I don't know if Desmos shows it a little bit better. It could be with the window I have set on the graphing calculator, but this is what this graph is. This is what the graph is. Okay. So now what we need to do though is we need to go ahead and come up with some kind of some scale, and that scale, or rather some points that we can take off here and plot. Like, what's the x-intercept here? 1. So that's one point that we know for sure, okay? And really, we don't need a lot more than that. Like, I can even just hit trace on my graphing calculator, and I can even see that at 2, it's negative 6.93. So even if I get a couple points on here, I can go with a couple points. It doesn't have to be perfect. It just has to give me an idea of what the graph looks like. So as Alana mentioned, we do know we have the point 1, 0. We have the point 2 and negative 6.93. Now, what about if I go into the before 1? Like roughly about a half. There we go, half. A half and 6.93 exactly. So another point that we have here is 1/2 and positive 6.93. And I'm going to stop there because I'm going to be honest with you. If you're graphing an equation like this on the exam, as long as you have a few points and you don't butcher the shape, you'll get the marks. So you don't really have to get too worked up about that, honestly. So if we went from I think I went from -5 to 5. So even if we go from -5 to 5, and for our x and y values, we even go up to 50 or whatever. I might not even do 50 on this. I might just do 20 and -20. Because what I'm going to do then is I'm going to plot those key points. Here is the x. Ooh, the x-intercept would be a little bit over. That's 2.5. That would be 1 here. At 2 and -6.93, that would be about there, and about a half, and positive 6.93 would be about there. So what that gives me is a pretty good idea of where I'm going. Now, I might, just because I'm a bit of a perfectionist, I might just go to 3 here, not for any other reason other than I just might want a little bit of certainty that I'm not doing this wrong. The only thing is, if I go to 3, I'm past -10. Well, that's okay. So it's about -11 at 3. So -11 at 3. So 3 would be right here. This would be 10. This would be -11. So you can kind of see what happens here with the values. And just because I'm curious, I'm just going to keep going. I'm going to go to 4. And 4 lands at -14 roughly. So if I go 4, I can go to -14. So we can really see that nice curve forming there. So we draw that nice curve in like this. And again, as long as your curve looks reasonable, you've got your arrowheads, then you're going to get the mark. So that's what -10 ln of x looks like. When graphs are marked on an exam, you must have a scale. You need to have labels. Now, in this case, we're not talking about a context or a word problem, so we're not writing down stuff like distance, time, money, that sort of thing. But if there's labels like that, they need to be present with units. And then you must also use the correct shape for the graph that you're drawing. And the more information you have, the better. So now that we've drawn that, what's the x-intercept, what's the y-intercept, what's the end behavior, and what's the domain and range? So what's the x-intercept? What's that? Yeah, the x-intercept? Still 1. What's the y-intercept? We still don't have any. What's the end behavior? Now, the end behavior is a little bit different. It's going to go from quad 1 to quad 4. What's the domain? Round bracket 0 to infinity. Range is. So besides the end behavior, there's no difference between this question and the last question in terms of these specific criteria. But if we look at the graphs, there is a bit of a difference because this graph is decreasing in value, and the last graph is actually increasing in value. Okay? So I've got one more set of examples for us to do, or one more example for us to do, and then it's time to get some practice. So here we go. We've got 4 graphs here, A, B, C, and D. And we also have 4 equations. -1/2 ln x, 2 log x, 3 to the exponent x, which is what we talked about when we did exponential functions, and 4 times 2/5 to the exponent x. So 2 of these are exponential and 2 of these are logarithmic. So help me out here. Which 2 are exponential? Ones that we looked at before today. Graph B and graph C, you say. B and what? D. If we're looking at the actual graphs themselves, it's graph B and graph D because they both go through the y-axis. Okay, so B and D are the exponential ones. So because this is a review kind of, so I'm going to talk about B first here. Which of those numbered equations is B? Yes, it is graph 4. Okay, and so then graph D would be what? What's that? Yep. So now we've got 1 and 2. Which one's graph A? Be careful. It's not 1, it's 2. Because it's increasing, right? If we take a look at the last example, there's a negative in front, so it's decreasing. And when we don't have a negative in front, then it's increasing. Okay? So this would be graph 2, and this would be graph 1. Okay? All right, your homework is on pages 482 to 487, numbers 1 to 15. Sure.